Hello. Going through the question I made. It's this one here. I'd recommend trying it before I go through it. So if you want to just pause and do it, and then press play when you're ready. So I'm only going to be going through part I and II in this one, but obviously at some point I will go through III and IV and V. Oh no, have I done this? Yeah. So we're going to start off with this first question. I just want to come to this saying what I'm going to be using quite a lot, and just to make sure that everyone knows what I'm using, isn't it? So if A is equal to, like, equivalent to B mod n, so like essentially the remainder, if B is the remainder, or when we divide A by n, and D is the remainder when we divide C by n, then multiplying them, the remainders is equivalent to multiplying the originals, and when you add them, that's meant to be an A. It's equivalent to adding the remainders when we're all working within this mod n. I mean, it's fairly trivial how to prove that, but I will not go through it. Anyway, so I'm going to start by going through II, and I will write the numbers, the Fibonacci numbers, each of which have been like just them modulus of 2. So we got 1, 1, 2, which is 0, 3, which is 1, but we can just continually add these two, the previous two remainders, as we've seen from this one. So we can get 1, 1, 0, 1, 1, and this is clearly periodic because given any 2, it repeats every 3, because what's it? It only this term only relies on these two previous terms. So given any 2 terms from that point, it will repeat again. Anyway, so we can show in the first n Fibonacci numbers, a third of them are going to be even. I mean, like, obviously depending on what n is, but I'm just, you know what I mean. It doesn't really matter. If you want to say depending if n is the floor of n or whatever, but I don't, n over 3, but I don't really care about that too much. So now for the 3, so we do the same thing, but this time we're doing it for 3 and then 4, which is 1, then 0, 1, 1. Now we got this 1, 1 again, and since these 2 terms repeat, we know that it continues to repeat onwards. So that is 1, 2, 3, 4, 5, 6, 7, 8. So every 4th one is divisible by 3, and if every 3rd one is divisible by 2, and every 4th one is divisible by 3, then every 12th one is going to be divisible by 6, because 12 is the lowest common multiple of 3 and 4. Actually, I can just go. I'll go into this. Alright, that was alright. So this is where it gets a bit more difficult. I mean, I tried to write this in the best way I can, but it's essentially saying just if you write this sort of sequence, but for any n, for any x in this case, I've written x, what is the point at which it starts repeating? So where you get this 1, 1 term, so that thing there, which is 8, or here, which is 3. Alright, so show that if any SNA equals CA, yeah. Alright, so for instance, I will explain what I mean by that. So, I've already explained here. Oh no, I haven't. So for instance, I would expect given this, I'm essentially proving that, for instance, S9 is going to either be 24 or 8 itself. And the same for like 2, because we got 2 is 3, 4 will be 6, 8 will be 12, and so on. Alright, so I'm going to begin by writing this. I'll write the terms of this sequence NA. When I mean the terms of sequence NA, I'm writing the Fibonacci's numbers mod this NA. So it starts like this, 1, 1, and then there's a few more, and at some point, so it's a Cth term. The Cth term, it will get to 0 here, and the previous ones will be -1 and 1. Just like this -1 is whatever, so NA -1, but I just call it -1 because the remainder is -1, whatever. But we can also call this A and B, and let that be equal to A plus B. Oh no, I'm being silly. No, I'm getting ahead of myself. I wasn't paying. I meant to write. I thought I was doing the end play. And if I write this equivalent sequence, we're going to get to 1, 1, ... and then instead of this being a 0 here, it will be some multiple. We should call it P. P1 n to the A, because it doesn't necessarily, I mean, P could be n, in which case it would be 0, but or any multiple of n, but in this case we'll just call it Pn, and the previous ones we'll call A and B, but they are just going to be some multiple of Na minus +1 and some multiple of Na minus 1. Alright, so I'll just begin by writing A plus B equals P1 NA. Okay, probably should have practiced this first, but anyway, I'll call this C minus 1, C minus 2. Now, if we go to the 2C term, we'll just write a little ... here, ... and I will write 2C minus 2, 2C minus 1, and then 2C. We can call, actually, let's not go to 2, let's just go to some KC. So, KC. So again, this KC will be 0 there, it's going to be 1 there and -1 there, because this is still within the repetition, so it was repeated. But here we potentially get a new one, so we'll just call this PK n to the A, and we'll call this C and D. So if we were then to go to the PK, so essentially I'm doing an induction here. Why? Well, this K plus 1 C minus 2 term, K plus 1 C minus 1, and then K plus 1 C. We'll call this PK plus 1 n to the A. And what we're doing here is we're going to try and find out what are this term here and this term here in terms of C and D. So this term would be, in terms of C and D, would be C plus D, and the next term will be C plus 2D, and the next term will be, I'll write it down the page here, but ignore there's a ... here, but the one immediately, so KC plus 1, then KC plus 2, and so on, will be C plus D, KC plus 2D, and then again we're adding these two together, and as I'm sure you can see here, it's like we get ourselves two new Fibonacci sequences, in terms of D and C, because we are just adding these two previous C's together to get that one, and these two previous D's together to get this one, and we can see that it's they correspond to one ahead. The C's correspond to one ahead of where it would be. So if I was writing the Fibonacci, if we call this the 0th term here, then the first term, then the second term, we see that it's 1, then 2, then that one's 1, 2, 3. But that one, if we start from this point for the D's, we can just see each term of C and D correspond to the Fibonacci sequence 2. Well, for C it's 1 ahead, and for D it's 2 ahead. So this one will be C, and this is where we come back to our A plus B, because it will be 1 ahead, so we get C, well, A plus B, and then this one, next one will be D, 2B plus A, making this one, oh no, I'm being stupid, ignore me, I miscounted. Alright, so I'll just write in this term, because we can ignore these terms. In fact, it doesn't even matter, we can just say, okay, so the one 2 ahead would be, because this C minus 1, C1, it will be whatever this term is here, and so that's A plus B, A plus 2B, and 2A plus 3B are the next two terms. So this one will be going to C, A plus 2B, and plus D, 2A plus 3B. And I mean, we can backtrack here and work out what these two are, but it's not so, at this current stage, it's not important to. So this is what, given that PK n to the A equals C plus D, is equivalent to C plus D mod n A plus 1, P to the K plus 1 n A, I'm sorry for the horrific handwriting, I'm writing with a mouse, C A plus 2B plus D 2A plus 3B, and mod, and I'm just going to write ditto, it's all in the same, mod NA plus 1. Alright, and then I can combine this thing to rewrite it as A plus 2B. So I can write C, A plus, C plus D, ignore me, I can't factorize these, C plus D, A plus 2B, plus D, A plus B. That's just rewriting this in forms of, so we get C plus D, A plus 2B, and then we're taking A plus 2B, lots of D, and adding it to that, and then just keeping the remainder, which is A plus B. Alright? And we know that C plus D was PK n to the A, what it was equivalent to, and A is equivalent to some, we'll come back to that actually, A plus 2B, and we know that A plus D is that, and A plus B was P1 n to the A. Yep. And now what we can do here is notice that A plus 2B, since A was minus, like, 1 less than a multiple of n to the A, and B was 1 more than a multiple of n to the A plus 2B is going to be 1 more than a multiple of A, because minus 1 plus 2. So, but obviously they can be different ones, but it doesn't really matter. We'll just call this I can call it any constant, can't I, really? let's call it like W, why not? And where W is some integer, it doesn't matter, I just call it W1, so I can call this one W2. So W1 n to the a plus 1. And we can do the same for D, because we know that D again is one more than but it can be a different one. But W2 n to the a plus 1. It's not saying that these are in any way linked. Well, they are linked, but it doesn't matter if they are or how they're linked. I will just rewrite this as that. And now if we times p to the k na times w1 n to the a, that is going to be a multiple of n to the 2a, which makes it a multiple of 2 to the na plus 1 for all a, so it doesn't really matter. So that is then equivalent to 0 when we're working with mod na plus 1. And so we're just timesing by this 1 here, so this is all equivalent to pkna. And the same thing happens here. When we times by this na term here, we get that is equivalent to 0, because it's going to be 2a, and even if a is 1, na 2a is still equal to a plus 1, so it doesn't matter. So that all cancels out, and that is all equivalent to p1 n to the a is equivalent, and I'll just write the bottom term here again, which is pk plus 1 n to the a. So we found that this is now each term given one term, given a term of k, so this can be any integer, that the next term will be that term plus that term if we're working with all of the terms of mod n to the a plus 1. And since we know n is prime, we're essentially waiting for this the point at which the term becomes 0, so the kth term is 0, is when this pk is a multiple of n, because then it will be na plus 1, and then that will go to 0. But since n is prime, if p1 is anything but if p1 is anything but a multiple of n, it will take n terms for it to be divisible by na plus 1, because we can just rewrite this as p to the k is na is equivalent to, I mean, we can get rid of all these na terms, to be honest, so I'll just write p to the 1 times k, if k is like the term. So for instance, the second one, the 2th term is pk, na, and so on. So we're waiting for this k to be a multiple of n, because we know p1 won't be because it's prime. So there's nothing other than a multiple of n that we can times it by, which would make it divisible by, and which would make pk divisible by n. So at the nth term, there will be essentially the first 0 after the repeats of there can only be a repeat at this term and no previous terms, because all other terms will be some other multiple times n to the a, and they won't be a multiple of n, making it not 0. So now we've shown that the first 0 occurs at the nth term or the first term. If p1 is just divisible by n, then this whole thing it's just, yeah. If that one's 0 and b is 1, then it repeats the same, has the same repetition, which is why I've included this term here, where it's equal to c. I mean, I couldn't find a way to prove that this statement wasn't true. If you can, I mean, leave it in the comments or something. I can manage to show it, because I couldn't find a reason that P1 was necessarily not a multiple of n. I'm sure there is a reason, but I couldn't think of it. So that's that, I suppose. And so I'm going to ignore this other bit because it's not really important. But I mean, if you can prove that that's wrong, that's good, I suppose. Yep. So now we've shown this as 0, but what if, for instance, it's a 2 here before the 0, and then that's 2, 2, which means it's not a repeat. So to show that this is, there can't be a repetition before this nth point, the nth c, but it doesn't necessarily mean that nth c is a repetition, because this previous number could be 2, it could be 3, whatever, and in which case it will not be a repetition, it'll just be there as a 0 there. Alright, so in this case we go back to our c's and d's here. So instead of working out this term here, we're going to work out this term, and it will just be going back one step, so c a plus b and plus d a plus 2b. Alright, so I will just write that as if n, what did I write? Okay, if k c minus 1 is equivalent to d k c minus 2 equivalent to c, then k plus 1 c minus 1 is equivalent to, well, I've actually messed up, c a plus b plus d a plus 2b. And when I say equivalent, I should be writing the mod n by the side, but just whenever I'm writing this equivalence, just assume that it's always in terms of mod n a plus 1. So again, we got the a plus b, which is equivalent to that. The a plus b is actually easier because that's already known to be that's just some, we'll call this w, we'll call it w3. W3 n to the a, and c is some constant w4 n to the a, and c was minus 1, isn't it? No, yeah, c is a minus 1, n to the minus 1, and then w3 n to the a, and then we have d. Actually, I think I'm going to leave d like it is now, but I will replace it with a plus 2b, which is 1. Actually, have I done this correctly? I think maybe I haven't. Or maybe I've done something stupid. No, as in this is fine, but I just got to try and think of the best way to factorize this. A plus b, that factorizes 0. That's just, oh no, because that's not, I'm being stupid here. Yeah, I didn't, yeah, ignore me. This bit's fine. It's better if I factorize like this again. Sorry, c plus d, a plus b, and we then get db, which is actually a lot better. So because this a plus b is a multiple of n to the a, and c plus d is a multiple of n to the a, because that's what they define. They add up to this term and that term. When we multiply them, they're going to be a multiple of n to the 2a, which means they're a multiple of n to the a plus 1. So that's equivalent to 0. So we then get that's equivalent to db, and therefore each time we can then get from that, we're saying that nc, kc minus 1 is equivalent to c minus 1 to the power of k, because if we think about d starting off as b, then that's b squared. So the second one's b squared, then the third one will be, we're essentially using induction. We're using induction again to get, so that's the first one squared, then we're times by b to get to the, so on, and then so for the kth one it's just going to be this one to the k. Alright, and from this, since we can get, we're going to do something to show that this one, so given when kc equals, so when this one equals 0, it's after n terms, so this is the nth term, so nc equals 0. So when we're doing c minus 1, the term c minus 1 term, so that's b, we'll call that b to the n, is the one previous to this nc term, and if that is 1, then we know that there's a repetition because it'll be 1, 0, and then therefore that one's 1, and now we have these two 0, 1 terms, we know there's a repetition. So if we rewrite b as some, okay, we'll go to w5. Like, I mean, this is not particularly, I mean, the maths is there, but I mean, I've been very sloppy with my constant naming, but all w's are integers, all w's subscripts are integers. I just can't be bothered to write that out. So we get w5 n to the a plus 1. Oh no, we already defined b as, I mean, we already had it as w1. No, no, it doesn't really matter. Okay, so it's just some constant times n to the a plus 1, and then we're going to the n because we're finding the nth one. And just by a binomial expansion, like this is going to be times, that one's going to be to the n, wa to the na, which is going to be that. So for every single one, we're squaring it, cubing it. The only ones which, the terms where the coefficients, the what ones, oh shush, man, ignore the alarm. The only terms which are going to have not be greater than n to a plus 1 or whatever, because it'll be n to the na, n to the n minus 1a, so on, until we get to n to 3a, then n to the 2a, then n to the a, and then plus 1, because it'll be 1. If we go in reverse, we'll get 1 plus some n to the a times some coefficient, and we know this coefficient to be n by the binomial expansion. And then after this, it's going to be n to the 2a times some coefficient, which doesn't really matter. It was because that's already going to be divisible by n to the a plus 1. But this one term, since this one's n, but for all other ones, say this is k. This is k to the na minus what n to the a plus 1. In terms of k to n plus a plus 1, there's this k here, which we know that, oh, how am I going to phrase this? Yeah, okay, this k is not divisible by n because it's less than n, because for all ones previous less than n, so the ones we're going up to, it's not going to be, this term here is not going to be 1, equivalent to 1, but since this is n, that we can rewrite this as n to the a plus 1 plus 1, and n to the a plus 1 is just 0, so that's going to, therefore that one is 1. And now since we have shown that this the nc term is equal to 0 and the nc minus 1 term is equal to 1, then the nc plus 1 term is equal to, and again this is all terms, I mean nc is not equal to 0 or whatever, but I've just, this is bad, this is bad maths, but the principle's there. The nc plus 1 is equal to 1, and therefore we've shown a repetition. So it repeats after nc terms. So come back to the previous question. We have answered this question, and when it's this case, if the first time round it repeats. So if the coefficient of the n to the a is a multiple of n, then it will just repeat the same anyway. But other than that, it won't, and it will be n to the nc. I couldn't find any examples where this is the case. The s n to the a plus 1 equals c. I couldn't find any examples. I couldn't prove that there was an example, but I couldn't also prove there wasn't an example, so that's why it's in, but it's fairly irrelevant. But I couldn't not prove it, so that's that, and at some point I will do part IV and V. Goodbye.